and welcome to another tutorial. In this tutorial, I'm going to show you how to add a-value constraints in SoFi for running constraint PMF. Constraining your PMF solution can be a powerful tool, especially when unconstrained PMF leads to mixed solutions that are difficult to separate. When performing PMF, often one has some prior information, knowledge, or expectations about the contributions of certain sources. For example, for a measuring site next to a busy street, one can expect a traffic factor in the data. Now, the a-value constraints help to incorporate this prior knowledge into the model. This can improve the model's interpretability and ensures that the solutions are physically meaningful. A-value constraints can be applied to both time series or profiles, but should never be applied to both at the same time. For time series, a-value constraints help to ensure that the temporal pattern of a factor contribution follows a certain trend, while for the factor profiles, the a-value constraints help to constrain the chemical composition to known source profiles. So, to put this in more mathematical terms, I have here the equations that describe the a-value constraint on the top for the factor profiles and on the bottom for the factor time series. We use the term F here for factor profiles as it represents one row of the factor profile matrix F, and G for the factor time series corresponding to a column in the factor contribution matrix G. The user inputs one or more factor profiles, Fj, along with the tightness of the constraint defined by the scalar A. The same, of course, goes for the constraints for a factor time series. The A value determines the extent to which the output F, so F solution, is allowed to vary from the input Fj and ranges from 0 to 1, with 0 meaning that the output has to be the same as the input, and with 1 meaning that the values may differ up to 100% from the initial value of Fj. So let's dive into a practical example. We start here in the orange PMF options panel. To follow this example now, you should know how to set up everything for an unconstrained PMF run, and you should also have imported at least one external reference profile. If you don't know or want to quickly refresh your memory on how to do those two things, I link the corresponding tutorial videos below. So we now leave the General Settings tab and go to Model Matrices. In Model Matrices, what you see first is the seed values that are defined at the moment. In this table down here, you can see the model matrix for profiles and for time series. At the moment, we still have the same settings as if we were to run unconstrained PMF. You can see here that all cells in this table are set to R meaning random. This means that each time PMF is initialized, a random seed value will be chosen for each cell of the matrix. Now, if we want to introduce constraints, we first need to tell the model where to start from, and for this we need to define a seed value. So we go over to this second window here, and first we select for which factor we want to introduce a seed value. So I start with factor 1. Now we have here a few options. So random means that no seed value at all is set, and that is what you typically have when you run unconstrained PMF. There is an option for pseudo-random. This can also be used for unconstrained PMF, and while random is fully random for each time you initialize PMF, pseudo-random is only random the very first time, and then if you have several repeats for a PMF run, it will use the same seed value as in the first PMF run. Then we also have the option to set a seed value to 0, which is useful if you have PMF over data that is from several instruments and you want to have one factor only being present in one or the other instrument. But what we're going to use is from vector. We now have to select which reference profile we want to use. Here, under external vector, you have a list of all previously imported reference profiles, and you can select any one of them. For this example, I'm going to use the HOA profile from Kripa et al. Once you select the external vector, you see a graph appearing here, and it can be used as a verification tool to ensure that the correct profile has been selected. Next, we have to select which variables we want to use for the seed value. So you have the option to either use a single variable, as listed here, or all variables of external vector. Since we want to constrain the full profile in the end, we're going to use all variables of external vector. As you can see now, the graph has updated, and you will see that all variables that are going to be used for the seed value are now colored in red. There is one more option before we can write the seed value into the model matrix. There is an option to normalize or non-normalize the reference profile. Since it's slightly faster to use normalized profiles, you can use the normalize option. Since the process of defining seed values and A values is additive, meaning that you can use several reference profiles to do so, you might want to use the non-normalize option in such cases. But in this case, we use the normalize option, and now that we defined everything, we can click here on Write into Model Matrix. As you can see, the model matrix has now been updated with the values from the reference profile. You also see that this button here has turned green. It was yellow before, and now that it has turned green means that all variables have received a seed value. It is possible that after writing into the model matrix that this button is not turning green, which means that your external profile has different variables than your PMF input. How to deal with such cases, we will explain you in a separate tutorial video. In case you want to constrain several factors, you just repeat the process that we just did for other factors. For example, if you also want to constrain factor 2, we just do the same again for factor 2. With this, we now have set the seed values for factor 1 and factor 2, meaning the starting values for the PMF analysis. But so far, we have not selected any constraints, meaning that after the starting value, at the moment, the model is free to do whatever it wants. We want to actually have something similar as the used reference profiles in the final solution, so therefore we now need to select the A value. For this, we go here to A value, and we have a very similar panel again. First, we have to select which factor we want to choose the A value for. Secondly, we then can decide which kind of A value we want to apply to the model. So the most easy one, or the easiest to understand, is the exact A value. If you click on exact A value, you can select again either single variables, all variables of external vector, or all model variables. In our case, since we only use one external profile that also contains all the variables of our PMF input, all model variables and all variables of external vector are the same. But if you use several external vectors or some vectors that do not contain all the variables of your PMF input, you might want to select all variables of external vector. For this example here, I go with all model variables. And now we can just select a value. That means how much the solution in the end is allowed to deviate from our reference profile. An A value of 0.2 means that the solution is allowed to change 20% from the reference profile that we chose. These 20% can be either plus or minus, and also for each variable it can be a slightly different value. It's just the upper limit that it's allowed to deviate from. If you then click right into model matrix, you see that it is written again in the model matrix, and you see that in our case, this turned green again. The next option that we have here is the sensitivity analysis. The sensitivity analysis means that SoFi will automatically loop through a range of A values. This is very useful when you're at the beginning of your PMF analysis and you need to make sure whether a reference profile fits, and also like how much your solution is allowed to deviate from the reference profile. So what you need to select here is you need to give it an initial A value. So typically that is 0, meaning that the solution is not allowed to deviate at all from the reference profile. And then you can go with the final A value up to 1, meaning that the final solution is allowed to change up to 100% from the reference profile value that you give. Then you also need to give it a delta value, which means in which steps the A value range should be scanned through. So once you define that, you can also just write that into the model matrix. And as you see now, it has also updated what we selected for factor 1. The sensitivity analysis is available in different dimensions, which means that if you have more than one factor that you want to constrain, you can have independent sensitivity analysis for the different factors. So if I select now factor 2, and I would also choose first dimension sensitivity analysis, both of the A values for factor 1 and factor 2 would always be the same and change the same. However, this will not cover the whole possible A value combination range. So you can set here a second dimension sensitivity. And with this, you can cover the whole possible range of A value combinations for those two factors. We also have an option for random A value. Select this, and just to show you, for the random A value, that is typically used in a much later stage of the PMF analysis, where you also can combine it with rolling PMF or bootstrapping. And here you also give it a lower and an upper limit and a delta value, and then the model will choose a random A value within those limits each time PMF is run. This makes most sense if you have a lot of repeats. Otherwise, it doesn't make so much sense, since you do not have any control over what kind of A value is selected. And then we have one last option here. This is rarely used, but it's possible to also pass limits directly to the ME2. This can be helpful if you do not want to have a symmetrical limit as you have with the A value approach. If you click this here, you actually have to provide a wave with your own limits to SoFi. Once you're happy with your A values that you set, you just need to make sure that you enable the A value constraints, and then you're ready to run. You will see at the moment I have here chosen 4 to 8 factors with 1 PMF call per factor, but since I selected the sensitivity analysis, SoFi will automatically scale the number of PMF runs accordingly. As you can see, this example would now involve 605 PMF runs. If you want to start your PMF analysis, just click yes, like you did with unconstrained PMF, and SoFi will run the full analysis. I also want to show you how to do the same thing for time series. So you go back to model matrices, and In the example we just did, we always used a factor profile to constrain to, which is the most common type of constraint. However, it's also possible to constrain a time series, and for this you simply have to switch here to time series, and then whatever you do will be a time series constraint. The principle is exactly the same as for profiles. Just one really important remark here, make sure that you do not constrain a factor, profile and time series wise. So while it is possible to constrain one factor with a profile and another factor with a time series, do not constrain both for the same factor. This will not work out well, since the model will not be able to apportion the proper concentration or intensity. There's also a few more remarks, tips, or tricks that I would like to give you on the way. So, before applying any A-value constraints, ensure that you fully understand their role in guiding the PMF model. I linked you some literature below in the description in case you want to read up on this. While the proper use of A-value constraints can significantly enhance the accuracy and interpretability of your source apportionment results, the wrong use or the introduction of unrealistic constraints can significantly degrade the quality of your results. When you do your PMF analysis, ideally you always start with an unconstrained PMF, and if the solutions are not satisfactory, then slowly start to introduce your constraints one after each other. This approach allows you to monitor the impact of each constraint on the model's performance. Plus, what we can observe quite often is that constraining one factor also cleans up other factors. Furthermore, you should keep in mind that over-constraining the model is a thing. Using too many constraints can reduce the model's flexibility and potentially lead to unrealistic results. So for your constraints, always begin by using A-value constraints on factors where you have the strongest prior knowledge about. Keep in mind that certain sources vary more in their chemical fingerprint than others. For instance, biomass burning emissions can vary significantly depending on the fuel used and the burning conditions. So the reference profile that worked in one place might not work with the same tightness of constraints in another location. So try different reference profiles. Furthermore, it's strongly recommended to constrain only primary sources, as secondary emission sources exhibit higher variability even when found present in a previous study at the same place, and this is due to the rapidly changing environmental factors that affect the aging and other chemical processes. Finding a good PMF solution is an exploratory process, even more so when constraints are involved. Too small A values may overly restrict the factor, while too large A values may provide too much freedom, nullifying the constraint's purpose. Take advantage for this here with the sensitivity test in SoFi to get a sense of what is reasonable for your data and adjust it based on the model's output to have an appropriate balance between flexibility and constraints. And just as a reminder, PMF is an iterative process until a good environmentally reasonable solution has been found. So don't be afraid to take a step back and go over your constraints and your reference profiles or time series again, as this part of the analysis can take some time, but it's also crucial for the final results to do it properly. Thank you for following this tutorial today, and hope to see you back soon.